All right. Hello. So I decided to just re-record this problem that we talked about on Friday. Since I forgot again to record, I'll try to remember to record our recitations when I can. We were talking about using method of characteristics to solve this initial value problem. So the first step in using method of characteristics is to construct the characteristic ODEs. So we'll start by constructing the ODEs, okay? And we can just kind of read these off, right? So dt d tau, okay? T is our first, call it our first independent variable. X is our second. U is our dependent variable. And we're going to map these to these characteristic parameters, and then Z, which is just going to be our solution in terms of our characteristic parameters, okay? So the first of these is T, and we can, because the PDE is in this form, right, it just has coefficients, variable coefficients in front of U sub T and U sub X. And then dt d tau is just 1, okay? And if we look at our initial condition, then we can read off our initial condition for the characteristic ODEs. T is just 0. So T is going to be 0 throughout. Okay. So X is going to be our dependent variable that varies on our initial condition. And its right-hand side, or the characteristic ODE, is going to be minus xt, and x0 of s is going to be, well, we can just parameterize x as s. And lastly, z is going to be our proxy for u. Its right-hand side for dz d tau is just going to be 0, and z0 of s, well, that's going to be this right-hand side here, so f of s, okay? So the first thing we want to do with these ODEs is to check invertibility. And to do that, we construct our Jacobian and take the determinant, okay? So remember that, right, like this, T sub tau, T prime 0 of S, okay? And making a mess already. Okay, so T0 prime of S and T sub tau x0 prime of S and x sub tau. Okay, so in our case, T0 prime of S is just 0. X0 prime of S is 1. T sub tau is 1. And x sub tau is minus xt, but remember we evaluate these at the initial conditions. So we get minus s times 0, or just 0. So we have minus 1, which is not equal to 0. So indeed, we have invertibility, okay? So now let's solve the ODEs, okay? Start with the easiest one, which is t, right? Integrating this up, I get tau. So just t equals tau, okay? Now, the next easiest one is just dz dt tau, excuse me. So I get z d tau equals 0, right? So z is equal to just some function of s, and our initial condition tells us what that is. It's f of s. So z is f of s, okay? Just like, sorry, just to back up over here, right? dt d tau equals 1, that implies that t is equal to tau plus some b of s, okay? But our initial condition here tells us that b of s is equal to 0, okay? So that goes away. So that's how we get dt, t equals tau, okay? Lastly, dx d tau equals minus xt, okay? But we already know what t is, right? So that's minus x tau. Now we're in a separation of variables situation. So we have the integral of dx over x equals minus the integral of tau d tau. In other words, log of x is equal to minus tau squared over 2 plus some constant of s, right? So if we plug in our initial condition, then we get log of s is equal to c of s, okay? Or at the end of the day, we get log of x is equal to minus tau squared over 2 plus log of s, okay? We're running out of space here. So let me write this on the next screen, okay? So we get log of x is equal to minus tau squared over 2 plus log of s. But of course, we can exponentiate this to finally get x of s tau is equal to s e to the minus tau squared over 2, okay? So let's pull all this together, right? We have x, we have tau, and we have z. Cool. So what do we need to do? We need to take these parameterizations of, t and x, and we need to invert them, okay? So this is easy to invert, right? We just get that tau is equal to, so as we invert, right? Tau is equal to t, okay? If I plug that in up here, I can invert that to get x. So I get x is equal to s e to the minus t, tau, t squared over 2, okay? So now I just need s in terms of x and t, which I can do just by writing s is equal to x times e to the t squared over 2, okay? So that's s in terms of x and t, and this is tau in terms of x and t, okay? So, but what needs to go in here is just s, right? So u of xt at the end of the day is z of s of xt and tau of xt, but it doesn't really even involve tau. So I have f of s of xt, which I have an expression for up here. So I get f of x e to the t squared over 2. Okay, so that's my solution. Okay, solved by method of characteristics. Okay, so that was our first problem here. The second problem was to really investigate what these characteristics here, right, or you could see them written as here, what they do to the initial condition, okay? So the main question was, okay, in part B, is to suppose f of x has compact support, okay? And let's even just define it, okay? Just on the open interval from minus r to r, okay? And we say for x not equal to 0, okay, what is the limit as t goes to infinity of u of x t, okay? And just to jump to the ending, right, and then I'll show you what justifies this. This is 0 as long as x is not equal to 0, okay? And remember, we used two main ways of justifying that, okay? So here's the line x equals 0, here's the line t equals 0, and let's say this is t increasing here, okay? So what we showed is that if you start here with an interval, okay, that goes from minus r to r, and only within this region, okay, do you have support, then essentially the characteristics x equals se to the minus tau squared over 2, okay, those are going to collapse in over time, right? And so all the region that's 0 is going to invade this region in the middle, okay, that is non-zero, and eventually this 0 region, or sorry, this region of support is going to shrink down to nothing, okay? Over time, it's going to vanish into the point x equals 0, okay? Now, to give a little more justification of that by hand, okay, let's jump to a clean slide. We can note that for all x not equal to 0, okay, in R, okay, as t goes to infinity, x times e to the t squared, okay, which is equal to s, increases, okay, or conversely decreases monotonically, okay, for x greater than 0, okay, or for x less than 0, okay? And as a result, okay, for some t tilde of x, okay, x times e to the t tilde squared over 2 is going to equal positive r, let's say, for x initially between 0 and r, okay? And in particular, t tilde is going to be given by 2 times log of r over x, okay? And this does live from 0 to infinity, okay? So over time, right, this particular function, right, which remember is the argument of this thing, where when that argument is outside of minus r to r, it's 0, right? So this argument, right, it'll always get to the point where it crosses through r. So another way of thinking about this, right, is that over time, right, if I start out with some, here's 0, here's r, maybe here's my initial x over time, as t increases, is going to cross through this point, right? And I'm no longer going to be evaluating this argument in a region where I have support, okay? So this would be my t tilde of x here. This would be my initial x here. And beyond this point, right, f evaluated along this curve, right, is equal to 0, okay? Because you're outside that region of support in that case. So essentially, once t is greater than t tilde, okay, then xt squared over 2 is no longer in this region, okay? So U is equal to 0, okay? And basically, a similar argument holds for X in minus over 0, okay? Therefore, in finite time, U goes to 0, okay? For any X not equal to 0, okay? So that's it, right? So remember, good intuition for this is essentially that this characteristic here, right? X equals S e to the minus t squared over 2. This is going to collapse down towards the point X equals 0, okay? But we've also justified it here essentially by saying this argument eventually is going to leave this region from minus r to r. Okay? So no matter where you start, even if you start very, very close to here, eventually you will leave this region in which you have support, okay? And so you will vanish in the long timeline. Okay, so that's the problem that we went through on Friday. I think maybe I'm providing slightly different example or kind of explanation than I provided there, but hopefully this complements our recitation session and at least gives you something recorded so that you have some reference to go back to. Okay, thanks a lot and see you all Wednesday.